open up a window here to share my slides. And hopefully you can see this first slide. Um, so what I'm going to talk about is this NASA mission that is called Lucy, and I'll explain why it's called Lucy. It's the first mission to what are called the Trojan Asteroids. If you don't know what the Trojan Asteroids are, don't worry, I'll explain that as well. I am the manager for the Lucy Science Operations Center that's based here at Southwest Research Institute in Colorado, Boulder, Colorado. And I also want to give a big thanks here to Hal Levison, who is the PI of the Lucy mission, and Kathy Olkin, who is the deputy PI, because I stole most of the content of this presentation from their presentations. So a big thanks to them. So let me talk about what Lucy is. So Lucy is sending a mission to a never explored group of asteroids. These asteroids are very old and they can be considered planetary fossils, and I'll explain why we call them that. But because they are like fossils of the formation of our solar system, we named the mission Lucy to honor the human ancestor fossil found in Ethiopia that was nicknamed Lucy. So this is a tip of the hat to the fossil Lucy, which was also named after the Beatles song Lucy in the Sky with Diamonds. So let me just explain what the Lucy mission is doing. It's going to these asteroids called Trojan asteroids. They've never been explored before. Hopefully you can see my cursor here, but what I'm showing is our solar system. These circles show the orbits of the inner planets, Mercury, Venus, Earth, and Mars. And then the gray dots are the asteroid belt. And these brown dots are what are called the Trojan asteroids. They are in the same orbit as Jupiter. There's a group in what's called the L4 cloud, the Lagrange 4 cloud, and then that leads Jupiter's orbit. And then there's a group in the L5 cloud, the Lagrange 5 cloud, that trails Jupiter. And these all orbit together. And you can see in this animation how that works. You can see our inner planets zipping around the sun here. And you can see these green dots of the Trojan asteroids that are leading or trailing Jupiter, which is this dot here. They constantly stay at this distance from Jupiter. Lucy, the spacecraft Lucy, was launched in October 2021. And the mission plan is that we are flying by some of those main belt asteroids. It's kind of flyby rehearsals. And then we're going to have 5 separate flybys of Trojans in the years 2027 to 2033. So this is a long-term mission. The prime mission itself lasts for 12 years. We were originally planning on flying by 6 Trojan asteroids, but then we discovered a new one, so we're flying by 7. Then we discovered another new one, so we're flying by 8 Trojans and 2 main belt asteroids. So this is the most asteroids visited for any space mission. Why do we want to go there? What is so interesting about these Trojan asteroids? Well, first of all, as I said, they've never been explored before. No one has ever seen one of these Trojan asteroids out at the orbit of Jupiter close up. And we believe that these Trojan asteroids hold clues to planet formation. They have very diverse colors from what we call gray to red. We think these differences date back to when these objects formed 4.5 billion years ago during the formation of the solar system. So all the different colors might mean that these asteroids were formed perhaps at different distances from the sun, and they were trapped into these orbits as the planet's orbits evolved. And I'll show you how that happened. But no matter the reason, we can't really understand what the Trojans are telling us. without looking at this diversity of color, reflectance, size, and all the other different properties that they have. So, what do I mean they were captured and maybe came from different parts of the solar system? So, I have here this little image that shows the sun and then Jupiter, Saturn, and the two outer planets, Uranus and Neptune, and then all these little dots that go from kind of a gray color to a red color. This is the leftover debris from the formation of the solar system. It's small objects like asteroids and comets and things that didn't form into planets. So it's the leftover bits of icy dirt that never formed planets and was left in the disk of the solar system when the solar system formed. We think the solar system formed in this way much more compact than it is now. All of these planets are much closer together. And here is an example of what we think happened. We think that the planets migrated out as they were orbiting around, and they scattered all these small objects. Some they scattered away from the solar system, some they scattered out in more distant orbits. And you can see here by Jupiter, there are some that were scattered into these Trojan Lagrange point orbits and got basically stuck there. We think this scattering happened something like over, on the order of 4 billion years ago, and they've been kept in cold storage in these orbits ever since. So we think that this is a collection of objects that formed in different parts of the solar system that got trapped in these orbits. So we can explore basically many different parts of the outer solar system by looking at just these Trojan asteroids. And just to give you an idea, here's kind of the before and after. And you can see how we think the planets, those giant planets, moved out. Jupiter moved in, and Saturn moved out, and Uranus and Neptune actually swapped places. If you see the dark blue object here and the light green one here, the dark blue is inside of the green one, but afterwards, the dark blue one is now further out. So we think that Neptune, which is the farthest out large giant planet, actually formed closer in. So studying these asteroids will tell us if this model, if this idea of the formation of the solar system might be true or not. Here's another way to look at it. So imagine you're above our solar system as it formed 4.5 billion years ago. Again, these circles show the planets. But now, again, these planets are Jupiter, Saturn, Uranus, and Neptune. And look at the dark blue circle is inside the purple circle. So the planet that's on this dark blue orbit is inside of the purple orbit. All of these green dots here is that leftover disk of debris from the formation of the solar system. So now I'm going to start running a model that shows the orbits, and you'll see how many millions of years are going by as this happens. And so you can see things are orbiting around, but they're mostly staying in the same orbits. Now watch what happens when we get to about 8.5 million years. So the orbits are changing a little bit, but nothing dramatic. Now we've hit 7 million years, 8 million years. Now watch. Boom. Suddenly those outer planets had an interaction in their orbits that made a very chaotic interaction, and they migrated out very suddenly, scattering all of those small particles away or trapping them into these resonant orbits like the Lagrange points around Jupiter. And notice, as I said, this dark blue orbit, which is Neptune, is now outside of the purple one. So this is what we call the Nice model, because the researchers were in Nice developing this model at the time, and it's planetary migration. And we think this is a model of how our solar system evolved after it was formed. So what that means is if you look at where the planets are now, so basically the x-axis here shows how far out the orbits are for each of the planets. And this is a logarithmic plot just to be able to fit everything in. And uh, you see here, starting from the left, there's Mercury, Venus, and Earth, which says you are here on Earth, and Mars. Then you have the asteroid belt here, the Trojans here that's orbiting around the Jupiter's distance. Then you have Saturn, Uranus, Neptune, and then this leftover belt of objects called the Kuiper Belt. Now, all of these small body reservoirs, the main belt asteroids, the Trojans, and the Kuiper Belt, were created during that formation process and the planetary migration. So we think that these are the leftover bits or the fossils of planet formation that never actually formed into planets. So if we study these small bodies, we are basically studying the building blocks of what created the planets in the solar system. And we can see what they are made of and the chemistry of what the solar system was like 4 billion years ago. We can't study that on Earth because the Earth has had all these processes with planetary changes in the crust, and volcanoes and crust activity and everything like that. So we don't have a lot of that original chemistry of what made the Earth, but these objects can tell us that. We have sent spacecraft to study almost all of these objects. This is a sample of the missions from the United States and Europe, Japan, other places that have studied these small bodies. And note that all of these small body reservoirs have been studied except the Trojans. The Trojan asteroids are the last unexplored class of these small bodies in the solar system. And like I said, they've been kept in cold storage for billions of years. So they really are fossils that will allow us to look back in time effectively and see what the solar system was made of and the small bodies were like in some of how it formed back then. So that is what the Lucy mission is going to do. It is going to go study those Trojans and find out what's going on out there. So we're going to study these Trojan targets in the L4 cloud, as I mentioned before. We have 4 targets we're going to fly by: Eurybates and its small moon Keta, Polymele and its small moon Shaun, Lucas and Orus. All of those are going to be flown. We're going to fly by in 2027 to 2028. Then in 2033, we're going to fly by a binary object, 2 large objects that are orbiting around each other in the year 2033. So this just shows we have objects with moons around them. These objects were observed the moons were discovered either using the Hubble Space Telescope or by stellar occultations, where the objects moved in front of a star and the star blinked out for a moment. And that allowed us to tell that there was this other object. Or again, with ground-based and space-based telescopes, we could see like these binary object of Petropolis and Menecius orbiting around each other as a binary. Eurybates is interesting because we think that this is a leftover remnant of a collision that disrupted a larger body and created a family of objects in the Trojans. And you can see in this animation here what happens when you had this collision and it spewed out all of this debris from the collision. And down here, you saw all these little leftover bits that were able to stay in orbit and create effectively a little moon. So we think that Eurybates and its small moon Keta are leftover debris from a collision. And similarly, this equal size binary of Patroclus and Menicius are going to tell us something about the earliest times of a solar system formation, because they probably formed as a binary. So all of these are going to be able to let us understand a lot of what the formation was like, from the colors they have, the sizes they have, and the different properties between them. So we'll have different colors. We will have different albedos, which is basically how reflective they are or how much light they absorb. So in this mission, we are really going to observe a wide range of properties of these targets and a wide range of sizes. I love this picture because this shows all of the small bodies that have been observed by spacecraft. And so these are comets, these are asteroids, these are objects out in the Kuiper Belt. Not shown are Ceres and Vesta, but you can see there's a whole range of sizes here that we had to send many, many missions to observe these objects. But with one mission, Lucy is going to explore this whole range of sizes. We have very, very small objects that are like Dinkinesh and the small moon Keta. We have slightly larger ones that are like the asteroid belt object Donald Johanson and the moon Sean. We have objects out in the Kuiper Belt and comets that are the size of Ptolemy. We have larger objects that are about 30 kilometers wide that we will see with Lucy. Eurybates and Oris are about 50 kilometers in size, and that's about the size of the asteroid Matilda. We have Patroclus and Menicius, that binary object that is as large as the asteroid Lutetia. So with one mission, with Lucy, we will be observing sizes across this entire range in just one mission. So let me talk a little more about those targets and how we're going to get there. So here are the Lucy targets. You can see Lucy is the red dot. The Earth is going to be the blue orbit. Jupiter is the green circle. And these white dots are the Lucy targets. So starting with launch in October 2021, we started off with the launch, moving Lucy off at over 27,000 miles an hour. And that launch from Earth, you can watch Lucy, the red dot there, get kind of kicked out. And it orbits, takes one orbit around, and it met up with Earth again for an Earth flyby, an Earth gravity assist. We used the Earth to do a little slingshot. We flew by Earth at about a speed of 34,000 miles an hour. And then we looped back in, and we're going to have another Earth swing by in 2024, coming up very soon in December. On the way out, we actually flew by an asteroid called Dinkinesh, which I will show you in a minute. That asteroid, or that Earth flyby, kicks us out a little more. We will fly by the asteroid Donald Johanson, which is named after the person who discovered the Lucy fossil. And then Lucy loops out to the L4 swarm, the fourth Lagrange point, where they're going to have 4 flybys in a very short amount of time. So in August of 2027, so coming up in just 3 years, we are going to fly by Eurybates and that small moon Keta. Keta is a moon named after Enriqueta Basilio, who carried the torch at the opening ceremony of the Summer Olympics in Mexico City. So a nod to the Olympics that is happening right now. After that flyby, we fly by Ptolemy in September. So that is just a month later, we have another flyby. And then 7 months later, we fly by Lucas in April 2028. And then finally, we fly by the fourth object in the Lagrange 4 cloud, Oris, in November 2028. So this is crazy. We are having 4 flybys in an incredibly short amount of time. And then Lucy drops back into the inner solar system, and then we'll have one more flyby of the Earth. That's going to help us loop out to our last target, the flyby of the binary Patroclus and Menelaus in March of 2033. So that is a 12-year mission from launch to our final target. After we fly by that, we are busily sending data back from the last flyby, but that is not the end of Lucy. Lucy is in a very stable orbit, and it will be able to do this orbit through the L4 and L5 cloud every 6 years. And it could do that for millions of years. Now, we're not pretending we're going to get funding from NASA to continue a mission for millions of years, but we could get an extended mission if NASA has the funding and the interest for us to do at least one more flyby of targets. So let me just give you a quick introduction to Lucy here. This is the Lucy spacecraft. It took more than 500 people to work on, design, and build and test Lucy, which was remarkably done during COVID. And we were able to do it under budget and on time. So that was a remarkable achievement for all the people working on this project. It weighs over 1,500 kilograms, over 3,000 pounds. Half of that weight is fuel. It has more than 3 kilometers of wires. It has to deal with very hot and very cold temperatures. It really is an incredible engineering achievement. And to get an idea of how big Lucy is, those solar panels, those round panels on the side, those are the solar arrays. Lucy is going to be the most distant mission that runs purely on solar power. It's because it's going out to the orbit of Jupiter, and it's running purely on solar power to do the mission. Even it loops a little past Jupiter. Those solar panels are about 24 feet in diameter. To give you an idea, there might be some people in the crowd. This will give them a better sense of size. If you're familiar with the size of a TIE fighter, it's roughly about the same size. So some people will see that and go, oh, okay, I know how big that is. What are we flying on Lucy? What are the instruments? We have a number of instruments that we are flying to study these objects. We have an instrument called Ralph, which has 2 different cameras. One looks in visible light with different colored filters. One looks in infrared light and looks at spectra. That will help us look at what the surface is made of and what the chemistry is. We have the TESS instrument, which is a thermal spectrometer. It will tell us the temperature of the objects. We have the LORI camera, which will take the high resolution pictures. And then we have something called the T2 cam, which is the terminal tracking camera. And this allows us to do basically autonomous tracking of the target. So when Lucy gets out there, the T2 cam will lock onto the target and track it, because we can't do tracking in real time. We can't joystick this. So this will allow us to plan all our observations and let Lucy automatically track the asteroid as it flies by at 1,500 miles an hour and take all the observations that we want it to do. And those observations will include things like understanding the geology from images. We will look at surface color and composition. We will look at surface temperatures and how much it heats up and cools down. And that tells us about the property of what it's made of, both on the surface and in the near interior. We can determine the interior by determining the density, and we can look for satellites and rings. So let me just tell you a little bit about those solar arrays. We have almost 8,000 solar cells on the arrays. As I said, it's the furthest operated solar power spacecraft from the sun. And when it launched, those round solar panels are folded up like a fan. And here's a movie showing how the solar sails unfurled in space after Lucy launched and created those beautiful round solar panels that you saw in the model. So those panels are actually on a kind of cloth. They're really impressive. Here's a beautiful image of the launch. It really was one of the most beautiful launches. People who've seen launches many, many times, and they're wonderful to see if you ever have a chance. You can see there was this low cloud deck and this arc. But what I want to show you here is this example of a launch. And this is just someone taken off by someone's phone. But I just want you to see. So here's the launch. You can see it light up, the main engines fire off, and Lucy is taking off. And you can see Lucy coming off the launch pad as this bright object lighting up the clouds from underneath. Really a beautiful launch early in the morning. And it's very wonderful. There's a delay in when you hear the sound. There goes Lucy, and then Lucy goes into the clouds. And this happens a lot. But watch what happens in just a moment here. It was just beautiful how it disappeared into the clouds and then came out again on the top. It really was a fantastic launch. And it was a perfect launch and got us exactly out at the speed and direction that we wanted to go. As I mentioned, Lucy had a close flyby of the Earth. It zipped in very quickly at about 34,000 miles an hour. It flew below the orbit of the Hubble Space Telescope and the space station. And it zipped right by and got us this slingshot to go on to the next part of Lucy's trajectory. We were able to watch from Lucy an eclipse of the moon. If you look very carefully here, here's the Earth on the left and the moon on the right, and you'll see the moon disappear. That was taken at the moment when the moon went into the Earth's shadow, and it was a lunar eclipse that we were able to observe from Lucy. And this is a picture Lucy took of now the Earth is on the right and the moon is on the left. And this is a very nice family portrait. In one image, it shows you the actual size of the Earth relative to the actual size of the moon and the actual distance between them. And you can see in these blown up images here, the Earth and the moon. This was great because it showed us that the cameras worked. Here's a picture it took of the moon during the flyby. All the cameras checked out. Everything worked beautifully. We also discovered after launch, we didn't know this before launch, that Lucy was going to fly by this asteroid called 1999 VD57. We didn't know that was going to happen. So we decided to plan a flyby activity after we had launched. This is very rare in a mission when you add a target like that, but it was going to take almost no extra fuel to do it. We called the object Dinkinesh, which if you look up Dinkinesh, say in Wikipedia, Dinkinesh is the Ethiopian name for Lucy. So it was a very nice name to call this asteroid that didn't already have a name. We thought that we were going to use Dinkinesh as just a practice. It didn't seem like it was anything of a special asteroid. We kind of expected it to be boring, to be honest, but it was going to be our first real practice with all the cameras and the spacecraft so we could shake out all the systems and everything before our Trojan flybys, but we got a lot more than just practice. We discovered that Dinkinesh, which is this big object here, had a moon. And you can see in this little animation here, the moon moving around Dinkinesh. So we did not know that this was a binary asteroid, that the asteroid itself had a small moon. But even more than that, let me show you the whole encounter movie and watch here as we fly in. Dinkinesh is in the middle and the moon is on the right. The moon will go out for a minute, then in and then out of the frame and back in. But look carefully here. I'm going to show you a zoom in on one of those frames. Look at the moon over here on the right. The moon itself is two pieces. We call it a contact binary. And this has never been seen before, that you have an asteroid with a contact binary moon. This is basically two asteroids that stuck together and created the moon. This was a huge discovery. It tells us a lot about the formation of objects in the solar system and in the Kuiper Belt. So this was a huge discovery, incredibly exciting for what we thought was going to be a boring flyby. So we named that little moon Salam. The International Astronomical Union agreed on that name. Salam is another fossil in the Lucy family that has been nicknamed Lucy's baby. Now, the Salam fossil actually did not live any time near around the time that the Lucy fossil person did, but it's been nicknamed Lucy's baby, and so we thought it would be nice to name Dinkinesh's small moon Salam. So where is Lucy now, and what is Lucy doing next? So you can go to this website. It is simply whereislucy.space. And you can go to that website and you can look at any time through the whole Lucy mission from launch till 2033, where Lucy is going to be, what it is flying past, where it is today, and you can see like what's coming up next. So this is a snapshot of today, where Lucy is. So Lucy is this white line with a white dot at the end. The red dot is Mercury, the red orbit and dot. The green orbit and dot is Earth. These white stripes with little dots at the end are the Trojan asteroids. And you can see like Donald Johanson and Dinkinesh are the ones in the asteroid belt. And you can see what's coming up next. In this case, Donald Johanson is going to be our next flyby in April, specifically on April 20th, 2025. So that's coming up very soon in just about 266 days. So keep an eye on the sky, come visit Lucy and see what, Donald Johanson we think is going to be just another boring asteroid. Let's see if that's the case or if it gives us yet another surprise like Dinkinesh did. So with that, I would just like to say, for those of you of a certain age, this I Love Lucy logo might look familiar. Those of you where this means absolutely nothing, go Google I Love Lucy. It's a 1950s sitcom. But you can also follow us on X, on Facebook, Instagram. You can go to the Lucy website at nasa.gov and nasa.surrey.edu. As I mentioned before, where is Lucy.space? And so with that, I would just like to thank you all for listening, and I am completely happy to take questions. Thank you. Right now, again, your audio is a little choppy. And if I can't hear a specific question, I may have to ask you to put it in the chat.
Okay. What is that? Did you hear that?
Okay. I absolutely did not. I heard you say, did you hear that?
Okay. Hold on a second. Yeah.
So if there was a question there, sorry, but I'm still not getting it. And I know it's probably hard. It's a great complex question and try to squeeze it into a chat, but we'll see what we can do. So what fuel is aboard? So we do have fuel. I'm not a prop engineer, but there are different kinds of rocket fuels, hydrogen and hydrazine and things like that that are used for doing trajectory corrections or orbit maneuver corrections. A lot of the time we use gyro wheels for pointing. So there are a lot of different ways we can either adjust the orbit or the fuel, but for the most part, we depend on the orbit that the spacecraft is actually on, just like an orbit of a planet or the orbit of a moon. That is the primary driver for where the spacecraft goes. And we use the onboard fuel just to kind of make the adjustments that we need to the orbit to specifically get to where we want. So that's why this whole tour, this whole orbit is so amazing, because we can do it with very little fuel.
Yes, does the tactical theory discovery of information.
Okay.
I heard the words formation and collision. So what does the contact binary discovery tell you about the formation of the solar system? Very good question. We are seeing more and more of these contact binaries. So the New Horizons mission, after it flew by Pluto, it flew by another object further away from Pluto, out in the Kuiper Belt, another billion miles away, that was called Arrokoth. And when we flew by, we saw it was also a contact binary. And we either by direct observation or by other methods, looking how the light changes when an object rotates, we think there are many, a large fraction of objects are actually these contact binaries. If that is correct, the only way to get a contact binary is if you have two of these big objects coming together very gently, like 1 meter per second, like walking speed. If they come together very fast, they just destroy each other, or one of them gets destroyed. We think that's how the Earth's moon formed, was a large, perhaps Mars-sized object collided with the Earth. All sorts of destruction happened. And in the debris, you had the moon form out of the leftover debris. So, but that does not make a contact binary. So what that tells you is that the relative speeds of these objects in their orbits had to be very gentle. The relative speeds, like you could be zipping down the highway at, 75 miles an hour, but the car next to you going the same speed looks like it's hardly moving at all. So you can have these objects in orbits moving very quickly, but it's basically just like that car next to you slowly drifts and then sticks to you. And that tells us about what was happening during the early solar system and how dynamically active these objects were. And then that goes into the whole discussion about that planetary migration I was telling you about earlier, that really throws things around and is incredibly violent and heats things up dynamically. So these contact binary objects had to form in a rather calm orbital environment. So that's one of the things that they tell you.
So, can you hear me, Joel?
Yes, I can hear you.
Okay, I think we're going to take one more question, then you get a break for 10 minutes.
That sounds good.
Sounds good. Any question? Yes, sir.
What would then conclude that there was planetary migration and that aging or switching of orbits?
I almost heard that, something about concluding and planetary migration.
Okay.
We're testing out your typing skills here. Okay. What led them to conclude that there was a planetary migration affecting Uranus and Neptune? So, when a couple different things. First of all, when we look at other planetary systems that are early in their formation, we see the central star, we see a debris disk, we see gaps in the debris disk that indicate maybe planets are there in the gaps, or we actually see planets around other stars. And we see quite a range of how close or how far the planets are and what the debris disk looks like. So we're pretty confident that our solar system formed like pretty much all the other planetary systems that we see, with this disk that extended out from in close to out to far distances, tens to, even out to 100 times or so the distance that the Earth is from the sun. So we think it must have formed in that way. And we see a lot of systems with large Jupiter-sized planets that are in very close to the star. So we know that that is a common way that planetary systems form. So if our solar system formed like that, it would be common. It wouldn't be unusual. There are other clues. If we look at those small body reservoirs I was talking about, the Kuiper Belt objects, and what their orbits are like, some of them are in an orbital resonance with, say, Neptune. Pluto is a good example. Pluto's orbit actually crosses Neptune's orbit. Now, in the billions of years the solar system has been around, anything in an orbit like that would eventually interact with Neptune and either collide or get kicked out of the solar system or kicked in toward the sun. Unless the orbits are in a resonance. In the case of Pluto, Pluto orbits around the sun 2 times, exactly 2 times for every 3 times Neptune orbits around the sun. So it's in a 3-to-2 resonance. That protects Pluto from ever having a close interaction with Neptune and can make that orbit last a long time. So we look at all the objects. There are many other types of those resonant orbits that are in orbits like Pluto or similar, and we look at how they got into those resonances, and there are certain ways you can capture objects in those resonances, just like objects were captured in the Trojan orbits. And the way to do that is for the planets to move out and slowly sweep up all the debris as the large planets move out and capture those small objects in those resonances. Finally, we also see objects that are on these very scattered orbits that just would not normally form in a calm disk around a star. It looks like something happened to them to throw them into really elliptical orbits. And the way to get those scattered orbits, those resonant orbits, and things like that is if you have this planetary migration. So we think that that happened. We think we can tell when it happened because it had to happen during a special time after Jupiter and Saturn and Uranus and Neptune formed, but before other things happened in the solar system. And we're putting together all these little pieces of a puzzle, all these little clues that point to the same answer. So, I don't use the word consensus or 100% certain because we don't know. But what we have is consilience. And consilience means we have many different directions of investigation that lead to a common, consistent answer. So let me just give a takeaway here of when people talk about science and they want an absolute answer and they say there is absolute consensus that this is the way things are, it's actually not consensus, but consilience, that the weight of evidence from many different areas of research point to the same conclusion. And that's the same for climate change, for example. It's not just one model. It's not just one study of the atmosphere, but many, many different areas of study that taken all together point to the same result. So with that, that's how we think the solar system probably formed 4.5 billion years ago. We may be wrong, but all the pieces of evidence of that jigsaw puzzle are telling us a similar story. And Lucy is going to help us put together a few more of those pieces. So thank you very much.
Thank you.